Hello everyone, and welcome to my talk on TRAIT2D, a software for quantitative analysis of single particle diffusion data that I and my collaborators developed during the lockdown period and which I'm very proud to present today at this conference. Before we begin the talk, I'd like to acknowledge the support of the Biophysical Imaging Group at the Institute of Applied Optics and Biophysics at the University of Jena and at the Leibniz Institute of Photonics Technology, and the development team made by John, Maria, and Joel, with special thanks to Chris, Jan, and Bella, who contributed in different aspects of the code that I'd like to present now. So the main motivation for me and the development team to going into this project was to build an open access and user-friendly tool to quantitatively analyze single particle tracking data. As such, TRAIT2D needed to have some essential features. There is to be a tool to extract physical information from single particle tracking datasets that would allow a user to go from tracking particles on time lapses to the data analysis with relative ease, with the possibility also of generating simulated datasets for model training, comparison with physical models, or comparison between tracking algorithms, for example, that would be useful for any level of experience, both on the side of the single particle tracking, but also on the Python programming point of view. However, before we proceed further, you must keep in mind that we developed this tool around interferometric scattering tracking datasets. In interferometric scattering microscopy, or ISCAT for short, we don't suffer from bleaching, and we have fast sampling rates available to us with the high signal-to-noise ratio for the detection of particles, which means that we don't suffer from many of the problems that affect, for example, fluorescence-based single particle tracking. So the result of our development was a tool that we named, as you might have already guessed, TRAIT2D, for which we provide a link in GitHub here, and which comes with a good documentation that we have on a dedicated website, and in the form of a paper that we published on F1000 Research. And this tool is fully open source and is accessible on multiple levels from the side of the APIs, but also because we provided the graphical user interfaces that would allow a less experienced user to take full advantage of it. And we provide a documentation with example notebooks that can guide a new user to fully explore the extent of the capabilities of TRAIT2D. So in essence, what can TRAIT2D do for you? Well, TRAIT2D can perform the tracking of 2D diffusing particles from a TIFF stack. It can simulate trajectories and produce simulated videos of these trajectories. And finally, it can perform mean-square displacement-based analysis of single particle trajectories in 2 dimensions. So the first part of TRAIT2D is, of course, the tracker module, which allows the collection of the single particle trajectories from TIFF stacks of moving particles. So the particle is initially identified with a spot enhancing filter, for which we need to give the parameters in this section. And then the spots are further refined using the radial symmetry algorithm for 2D Gaussian fitting, which is very fast but assumes constant particle size, so we don't have an estimation of the size of the particle through this refinement approach. Then the trajectory linkage is done with an Hungarian algorithm, which is thus optimized for long uninterrupted trajectories. We can further select if the particle we're tracking is in a dark spot or a light spot over the background. We can run a pre-processing step, which would be equivalent to a background subtraction specifically. We can save and load parameters from previous tracking sessions to allow for batch processing of many different movies. We can preview the tracking and save a small portion of the full movie tracking to give a test to our parameters. And then finally, we can save data as a CSV file, meaning saving the multiple trajectories originating from the TIFF stack. And we can also save the movie in which the particles are tracked, as you see in the figure here. Further, we have the simulator module, which allows the user to simulate single particle trajectories through simple Monte Carlo methods. In this module, we have the diffusion class, which is an abstract class that can work as a template for different diffusion modes. And for example, we have implemented two already. One is simple Brownian diffusion, and the other one is hopping diffusion, in which we generate a compartmentalized environment as a Voronoi map, and in which a Brownian particle is diffusing with a certain probability of jumping from one compartment to the other, or hopping. Furthermore, we can save the simulated trajectories as movies through the movie simulator class, to which we need to feed, along with the parameters of the final movie that we want to obtain, a PSF which we generate with the Convolution Lab 2. And the results of the movie simulation you can see here on the right. So on the left you have the simulated trajectory with added Poisson noise, and on the right you have the result of the convolution with a simulated PSF. And finally we have the analysis module, which allows the extraction of physical quantities from single particle tracking data. So in this module we have two classes, track and list of tracks, which contain the single particle tracking data that we already obtained, and we can also feed custom data sets from other trackers, and contain useful methods for data visualization and quick analysis and statistics of our data. Then we have the model database, which contains all the plausible models to be fitted to the track data inside a class. So we have some predefined models that come with the software, such as Brownian diffusion, Hopf diffusion, and confined diffusion, and others. But we also have the possibility of defining our own models, and we have provided an example on how to do that. So the track and list of tracks classes contain in their variables, of course, the mean-square displacement and the apparent diffusion coefficient, that then the models contained in ModelDB can be fitted to with a simple least squares fitting routine powered by SciPy. And using these two methods, ADC analysis and MSD analysis, through which we can also achieve categorization of the tracks, estimation of physical quantities, and of course model fitting. And the categorization is done through purely statistical means. But of course, the work for TRAIT2D is not done, if it ever will be done. So we are thinking of new improvements to the tool, such as implementing a track explorer for quick summary statistics for each track that can be run on the instrument, support for different microscopy techniques, such as mean flux or TURF or other fluorescence-based tracking technique, and an improved simulator for better performance and, for example, dynamic maps on which particles can diffuse. And also we would like to improve the tracker by adding more tracking algorithms and improving the performance, of course. Additional data analysis paths, such as maximum likelihood estimation or some machine learning or deep learning powered paths, and some GUI redesigns, especially for the tracking and the simulation part. Of course, we have some future directions that we would like to explore with this project, such as, for example, integration as a plugin in softwares like Napari and ImSwitch that would allow to do so, to streamline the collection and analysis of the single particle tracking data, development of standalone application to be even more user-friendly and portable, and finally reaching for 3D tracking and analysis, maybe developing a TRAIT2D, we are not sure yet. But in any case, feel free to participate in the project or just give us any suggestion. We really like to check our GitHub page and find your suggestion and your feedback, and we're always very happy to help if we can. Finally, I would like to thank you all for your attention, and I hope you get a chance to try our software. And as I said already before, feel free to participate and let us know what you think. Thank you very much.